Section 4.4 on the mean value theorem.
Basically, there's two theorems that we work on in this section. The first theorem is used to prove the second theorem, and really the second theorem, which is called the mean value theorem, is the one that we really want to get at. And it has implications for later on and further on in math classes that you take. But first, let's just kind of understand what Rolle's theorem is saying. And then we'll do an example with Rolle's, and then we'll take a look at the mean value theorem. So Rolle's theorem says that if you have a function that is continuous on a closed interval, it's differentiable on the open interval, and the y values at the endpoints are the same, okay? And I'm going to draw this in a moment. If all three of these is true, then there's at least one number in that little interval, which they're calling c, an x value in that interval that has to have a derivative at that value equaling 0. So let's just take a look at one example of what this might look like. So we've got a closed interval like this, and we have a point here, a point there, and a continuous function maybe like that. And what Rolle's is saying, first of all, let's just be sure that this satisfies Rolle's. We have a continuous function, so that is definitely true, the way I drew it. It has no breaks, no holes, no asymptotes, no weirdness. It's differentiable. What does it mean to be differentiable? Well, it doesn't have a sharp turn, it is continuous, and it doesn't have a vertical tangent line. Anyway, and then f of a is equal to f of b, right? This y value here is f of a equaling f of b, right? And so what you'll notice is right here at this point, we end up with a horizontal tangent line. And so what Rolle says is somewhere between a and b, there's a c such that f prime of c is equal to 0, meaning we have a horizontal tangent line. Now it says there has to be at least one number c. So depending on the curve, you could have more than one, right? So another possibility where Rolle's would apply. So we have a to b. We have maybe f of a is right there, and f of b is at the same place. So again, f of a equals f of b. And maybe our graph looks something like this. And so now we have two places where we have horizontal tangent lines, right? So maybe this one is C1 and this one is C2. F prime of C1 is equal to F prime of C2 is equal to 0. We could also have a situation like this, where again, f of a equals f of b, and maybe it's just a horizontal line, right? Well, that means we have a 0 slope at any c between a and b, right? F prime of c is equal to 0. So these are all examples where Rolle's theorem applies, and that's what we get, okay? Now, what happens if we lose one of the three criteria? Well, then Rolle's does not apply, and then let's see what that looks like. So I'm just going to write if Rolle's hypotheses are not met. Okay, so first of all, what if it's not continuous? Well, can I come up with a counterexample where there is no c such that we have a horizontal tangent line? Well, here's f of a, f of b is the same. I could have a graph looking like this, where c would have been there at that maximum, right? But because f is not defined there, we're going to get f not continuous at C. So we don't have a horizontal tangent line anywhere, right? Because we have that hole there. So there's a situation where one of the hypotheses is not met. So therefore, we do not have Rolle's theorem to say there exists a C between A and B such that f prime of C is equal to 0. Do A and B need to be the same y value? Good point, Ethan. And it says that right here. F of A and F of B has to be the same y values. That's exactly right. And we're going to see what happens if we don't have that. We'll see that it doesn't. Rolle's theorem is not guaranteed. So here, if we have a situation where we're not differentiable, right? This is the second item here, differentiable on AB. What if we're not differentiable? Well, that could look something like this, right? And so maybe there's C, not differentiable at C, F not differentiable at C. So Rolle's does not apply, meaning we don't have a horizontal tangent line at C. In fact, there's no tangent line at C because we have that sharp turn there. And then finally, and again, here's F of A equals F of B. And here's F of A equals F of B. And so the last situation where we violate one of Rolle's hypotheses is exactly what Ethan just asked about. What if F of B is way up here and F of A is here? We could still have something continuous and differentiable, but it's not going to guarantee us that we have a horizontal tangent line, right? Actually, the way I drew that almost looks like it does. Okay, no horizontal tangent line there. So this is what happens when F of A, or this is a counterexample when F of A doesn't equal F of B. So again, we have to have all three of the hypotheses or else we're not guaranteed that there is a C, whoops. We're not guaranteed there is a value C between A and B such that F prime of C equals 0. So there's that. So now we're going to use Rolle's. Let's go ahead and just try an example with Rolle's. For the function f of x equals x squared minus 4x plus 1, show that Rolle's theorem applies on the interval 0 to 4. Then find all numbers C in that interval for which the theorem holds. So before we can do anything with Rolle's, we have to state that the three hypotheses of Rolle's are met. In other words, all this stuff in yellow, I have to make some comment to the reader. I'm about to use Rolle's theorem, and here's why I'm allowed to use it. Because 1, f is continuous on this interval, 2, f is differentiable on this interval, and 3, f of the endpoints are the same. So that's the first thing we're going to do. So I'm going to say f of x equals x squared minus 4x plus 1 is a polynomial. So f is continuous on the real line on all of R, and f is differentiable on the real line. Okay, to use Rolle's, you have to tell the reader, I know this is my function and it's continuous on the, really on the interval is what we care about, right? Continuous on 0, 4, but if it's continuous on R, it's going to be continuous on 0, 4, and it has to be differentiable on 0, 4. Okay, that's great. Now what? From there, let's say also notice, so now I've got to say something about the third hypothesis, right? The one you see at the very top of your screen there. I have to say something about f of A equaling f of B. So notice that f of 0 is equal to, well, let's find out, 0 squared minus 4 times 0 plus 1, which will equal 1, and f of 4 is equal to 4 squared minus 4 times 4 plus 1, which equals 1. So f of 0 is equal to f of 4. Therefore, Rolle's theorem applies. Okay. So before we actually do what Rolle's theorem says, let's make sure we're good so far. The question said, for this function, show that Rolle's theorem applies on the interval 0 to 4. We've done that. Now, the next part is they want us to find all the numbers C in the interval for which the theorem holds. So I'm just going to go off to the side here, maybe switch color. Now we find all C in the interval 0 to 4 such that f prime of C equals 0. Rolle's theorem guarantees for us, based on the 3 criteria that we just noticed, there has to be an x value between 0 and 4 where we have a horizontal tangent line. Okay, well, let's see, how are we going to do that? Well, why don't we go ahead and take the derivative. F prime of x, this is an easy derivative, right? 2x minus 4. And then we set it equal to 0. So 2x is equal to 4, x is equal to 2. So C equals 2, which is in 0 to 4 as guaranteed by Rolle's theorem. All right, so that is Rolle's theorem. And again, we use Rolle's theorem mainly to prove the next theorem. So mean value theorem. Now, this one is a little more complicated, but it all comes down to the picture. And once I draw the picture for you, I think you're going to be able to understand what it's saying. What I'd like to first notice is the criteria for the mean value theorem, kind of similar to part of Rolle's, right? We need f to be continuous. We have to have a continuous function, and we need to have a differentiable function on our interval. Okay, so continuous on our interval and continuous and differentiable on our interval. Now, if we have that, that's great. Then what? Well, let's draw the picture instead of just looking at this, and then I'll come back and explain. So I'm going to draw 2 points and a function connecting them. Maybe something like that. And so we've got this function f, and I'm going to call this a, and over here we're going to call this b. And so this is the point a comma f of a, and this is the point b comma f of b. Now, I'm going to draw a secant line here. Okay, so there's a secant line. Here is our function f. Okay, who can tell me how to find the slope of that secant line? Slope of secant line. Anybody want to speak up? Tell me how to find the slope of the secant line. Just think elementary algebra. Okay, Hansel has it, but let's use proper notation. What are we going to get here? Difference of the y's over the difference in the x's, right? So f of b minus f of a all over b minus a. Does that look about right? I took this y value, y2.
I see.
Minus y1, right? And
Yeah,
then
that makes sense.
x2 minus x1. All right, cool. All right. So that is the slope of the secant line, okay? Now, if you imagine all the different, this is so much easier to show in person, but imagine all the different tangent lines between A and B. I'm going to draw a few of them, but then I'm going to erase them. So there's a tangent line. There's a tangent line. There's a tangent line. There's a tangent line. There's a tangent line, right? They all have different slopes, but one of them is special. And that's the one we're worried about. That's the one we're interested in. One of them is going to be parallel to the blue line. Is that believable, first of all? Give me a thumbs up if that's believable, that there exists somewhere in there a tangent line whose slope is going to be parallel to the blue line. Yeah? Okay, cool. So let's go ahead and try to sketch it as best we can. So maybe something like that. Maybe right there is the point of tangency. And so we're going to call that C. Now, slope of the tangent line, how do I write that? How do we get the slope of a tangent line? You guys know this.
Derivative?
Derivative.
Derivative.
F prime at C, right? Totally good? All right, now watch. If we come back up here and look at the mean value theorem, it's saying if f is continuous on AB, I drew a continuous function f. If it's differentiable on AB, I drew a differentiable function. Watch what it says. The derivative at C, wait, that's the slope of tangent line, is equal to, guess what? Slope of secant line. In other words, backing up, assuming that the two criteria in yellow are met, then the mean value theorem guarantees the existence of this C here in purple such that the slope of the tangent line will equal the slope of the secant line. It guarantees it'll be there. Okay, this is what you call an existence theorem. They're saying that a C exists where the slope of the tangent line is equal to the slope of the secant line. That's what it's saying. All right, cool. Let's see. I'm going to go through the proof on this because it's one of the cooler proofs, and this is an important theorem for future classes. A little bit here. We're going to use it here a little bit, but let's write a couple things out. And this is kind of cool how this turns out. The equation of the secant line is what? Well, let's think about this for a second. We have to take y minus y1, right? Here, let's write it this way. Y minus y1 is equal to m times x minus x1. Okay, you guys are familiar with that. Well, let's grab the point A, f of A is our point. So I'm going to get y minus f of A equals, I need the slope. Well, guess what? In blue to the right there, I have the slope. That's f of A, or f of B, I guess. F of B minus f of A all over B minus A times x minus A. All that is, here, let me spread this out a little bit, is y minus y1 equals m times x minus x1. That's all it is. And I'm going to rewrite it this way. I'm going to add over f of A to get f of B minus f of A all over B minus A, x minus A plus f of A, like that. And I'm going to put a little star next to this because we're going to need it later on. All right. Now we're going to define a new function. Define the function g as follows. G of x is going to equal the f of x function minus y, and the y being the y above, right? So that's f of x minus f of b minus f of a all over b minus a times x minus a minus f of a. Just to be clear, we took f of x and we subtracted this whole thing in blue, right? And because it's two terms, you subtract each term. That's why I have a minus sign in front of the brackets and a minus sign in front of the f of a. So that's what I've done. So what we have so far is we wrote the equation of our secant line. Then we came up with a new function, which we're defining to be the black function in your picture minus the blue function, the secant line. As a matter of fact, you know what? Let's go ahead and make it blue, just so it's clear. This guy right here is blue. And basically, right here, we're subtracting off blue. And that's what y is. Y is blue. Okay, so Hansel's asking which part is g of x. G of x is a function that is not drawn on our graph. It is the function that if you take f of x and subtract the blue function from it. In other words, at each point, watch, I'm going to just draw and then erase this. For example, here, you would take the y value here and subtract it from the y value there. Okay, so that's how you would get a new y value. You would take f minus y, and that's how you're getting g. Okay, it's not drawn on here. That's the idea. Okay, we have to notice a few things. Notice that g is the difference of two continuous functions on the interval AB. So G is continuous on AB, and G is differentiable on AB since it is the difference of differentiable functions. Okay. One more thing to notice. Also, G of A is equal to 0, which is equal to G of B. Okay, now that requires me to at least show how I'm getting that. Okay, but it's actually not that hard to see. There are two ways of seeing it. One's fast, one's less fast. If I think about G of A, if I take my function right here, right, G of A, that would mean plugging in A in for all the x's. So G of A would equal f of A minus f of B minus f of A all over B minus A in brackets times x minus A. I'm sorry, that's A minus A. I'm putting A's in for all my x's. Minus f of A. And you'll notice very quickly that this becomes 0, which is going to zero out this whole thing. And then you get f of A minus f of A, which is equal to 0. Okay? G of B is going to look like f of B minus f of B minus f of A all over B minus A. And here we're going to get B minus A instead of x minus A minus f of A. Now this one's a little harder to see, but still not that bad because you'll notice that we can cancel off b minus a with b minus a. And when we distribute the negative, we get f of b minus f of b plus f of a minus f of a, which again is equal to 0. So what we have here is 3 statements about the function g. Okay, we said 1, g is continuous on AB. So I'm going to put a little 1 there. We have 2, g is differentiable on AB. And we have 3, g of the endpoints is the same. Hey, wait, aren't those the same 3 criteria we need for roles? So Rolle's theorem applies to g of x, right? So if Rolle's theorem applies, thus there exists C in AB such that, this is just the Rolle's thing, g prime of C is equal to 0. So we're going to have to take the derivative of g, which looks horrible, but it's not, right? I'm talking about our yellow function up there. We want to take the derivative of g, and it's got to equal 0 at C. In other words, I'm going to write 0 equals g prime of C, which is equal to over, okay, this is kind of cool. Watch this. This is our function g in green, right? So it's got to be f prime of C minus y prime. And the reason I can do this is it's just the derivative of a difference, right? Now, the derivative of y prime, y is really just a line. And you know the derivative of a line is really just the slope of that line. So this becomes f prime of C minus f of b minus f of a all over b minus a. This here in blue is slope of y, also known as y prime. And that equals 0. So if I were to add that over to the other side, I would have f prime of C is equal to f of b minus f of a all over b minus a, which guess what? That is our result from the mean value theorem that you see way up there at the top of your screen. Okay, so we did it. We proved it. It was a little bit of work, but we got there. So they give us a function, given f of x, determine whether the mean value theorem can be applied to f on the closed interval -1 to 1. If the mean value theorem can be applied, find all values c in the open interval -1 to 1 that satisfy the theorem. So to use the theorem, we have to have 2 things. The things in yellow, right? We have to be continuous and we have to be differentiable on the interval. F of x again is a polynomial and is continuous, I should say, so it is continuous and differentiable on R. So f is continuous on negative 1 to 1, and differentiable on negative 1 to 1. So by the mean value theorem, there exists C in this interval such that f prime at C is equal to f of 1 minus f of negative 1 all over 1 minus negative 1, right? That is the slope of the secant line, right? This is the thing in blue that I've been doing over and over again, right? That's the blue part. F of B minus f of A over B minus A, which that basically is equal to what? Well, if we plug 1 into our function, we're going to get 1 cubed minus 1 squared minus 2, minus, plugging in negative 1, we're going to get negative 1 cubed minus negative 1 squared minus 2 times negative 1 all over 2. And I get that to equal what? Negative 2. I think that's negative 1 plus 1. Is that right? Negative 1 minus 1 is negative 2 plus 2 is 0. So that's going to be minus 0 over 2. We get negative 1. So that's the slope of our secant line. To find C, we're going to take the derivative, which looks like this, and we're going to set it equal to that negative 1. That factors. So x equals negative 1/3 and 1. Since C must be in negative 1 to 1, C equals negative 1/3. So we found another value, but we only wanted the one between negative 1 and 1, right? It says find all C in the open interval negative 1 to 1 that satisfy the theorem, and that's this. In other words, negative 1/3 is going to be the place where our function has the same slope as the secant line between the endpoints. Okay, so this is what our function looks like. And I can come up with my secant line between these points like that. And then we also found our C to be at negative 1/3, right? So I'm going to put negative 1/3 for the x and f of negative 1/3. Like that. You can see C up there. And then if I draw my tangent line, what should happen? My tangent line at C to this curve should be parallel to the line going through AB. And it sure looks like it is. Let's make it red so it matches our colors from earlier. And let's make this one blue. And so that's what we just did. We found C at negative 1/3, which is the location of the point on the green curve where the tangent line is parallel to the blue secant line.
So that's the idea with the mean value theorem. Go ahead and do the problems below.